Okay, so good afternoon, everybody. I'm Mona Maril. I'm representing the GRAPHERGIA Research and Innovation Project. And today I'm really happy to gather all of you to this third webinar session that we host together with the POLYGRAPH project that is dedicated to laser-induced graphene and MXenes for wearable devices. And without any longer delay, I would like to kick off the session for today to have the full hour of presentations that will be, of course, shared even beyond today's session. And so firstly, thank you both speakers that we are welcoming today. So firstly, we will hear from Professor Spiros Yiannopoulos, who is the GRAPHERGIA project coordinator, who will offer us a short introduction to the laser-assisted graphene process that we implement in the GRAPHERGIA project. Then we will give the floor to our keynote speaker, Dr. Marcos Pacenovic from the POLYGRAPH project, who will walk us through to the laser-induced graphene and MXene on biocompatible polymer substrates on sensors and electrodes. And at the end, we have 5 minutes for questions and open discussion. And of course, I'm Mona Maril. I'm from Australo Marketing Lab, and I'm leading the dissemination and communication activities of our research projects. So warm welcome to all of our attendees. I can tell you that this session has gathered participants, of course, across the European Union, since GRAPHERGIA is a EU-funded initiative, but also beyond. We have also participants from India, Turkey, and of course, Serbia, where Dr. Spasanovic comes from. And participating organizations, we can see that we have participants essentially from scientific community, but also beyond, from e-textile and battery producers, as well as graphene and e-textile industry representatives. And with that, I can also tell you that we have representatives from other graphene innovation-enabled sister projects that are also featured on the lower corner of the slide. So if you want to know more about the sister initiatives related to GRAPHERGIA that are deploying graphene innovation on other application areas, you can see them here. And I also welcome all of you in today's session. And before we start the actual presentation, let me just share with you that we are recording the webinar and it will be available on the GRAPHERGIA's communication channels. During and throughout the session, you can add your questions in the Q&A box in real time if you want. And then after the presentations, we can take the questions and discuss as many as we can within the time frame. And finally, let me just underline that we offer this session in the framework of GRAPHERGIA Hub. It's a hub that we have established within the GRAPHERGIA project, where we connect innovators from smart textile industries, next generation lithium battery industry, and graphene industry to exchange their know-how and experiences. And thanks for all of them who agreed to become a virtual member, let's say, of the hub. This way we can keep you posted of the next webinars that we will be organizing until the end of the project. And finally, what GRAPHERGIA is about. So we are research and innovation action funded by the European Commission. We run for 3.5 years, and now we are in the middle of the project, and we will run until the end of March 2027. In total, we gather 11 innovation and research partners from 6 European countries with the goal to develop a graphene-based materials to energy devices with the application areas of smart textiles and lithium batteries. But with no longer introductions, let me pass the floor to our first speaker, Spiros. So please go ahead, Spiros, and you can share your slides and take the floor.
Thank you very much, Mona. And would like also to thank Professor Marcos Pacenovic for accepting the invitation. I hope you can see my slide.
Yes, perfectly. Thank you.
Thank you very much. So welcome anyone in this meeting, everybody. So, GRAPHERGIA is a project, as Mona mentioned, that is attempting to develop pilot lines based on laser-derived graphene to produce energy harvesting storage devices. A very brief introduction about GRAPHERGIA. GRAPHERGIA is mainly focused on two main applications. One is on smart textiles. So the idea here is to transform the garment to a smart connecting hub between the human being and the Internet of Things to avoid the use of batteries and to harvest biomechanical energy, convert it to electrical, store it, and use it to wearable sensors. The second path of the graphene is about lithium-ion batteries. And the main focus here is to use again laser-based techniques to develop a dry electrode fabrication of anode materials based on graphene and nanocrystalline silicon for lithium-ion batteries. You can see here in this block diagram that, as I mentioned, the central point is to use lasers and develop this technology from the lab scale to the pilot line. So Ford is developing this technology and in collaboration with Adamant Composites SME are building together a pilot line for the laser-derived graphene on different substrates. So in the upper line with the red labels, you can see how the partners of GRAPHERGIA are dispersed across the various parts of the technology chain, from process optimization, from flexible devices to energy harvesting layers for the triboelectric generators, power management systems to transform these signals to a helpful, let's say, form of energy, and then companies that work with prototyping of the signal and the connection with IoT. And in the bottom line, you can see the other focus of GRAPHERGIA, the development of lithium-ion of anodes for lithium-ion batteries. The idea is to use low-cost raw materials and decompose them by laser at ambient conditions. And here the role of Plioni Energy is very important, where they try to upscale the process and prepare, let's say, in a large scale anode material for lithium-ion batteries. Actually, this is a very brief plan of the pilot line that is developed in GRAPHERGIA project in collaboration with Adamant Composites. You can see here that graphene can be prepared by lasers and can conformally, let's say, cover fibers, making the textile conductive. I will spend a couple of minutes for a very brief history of laser-assisted graphene synthesis, why this is important. Actually, the story started many years ago, in the beginning of 80s, where two groups, Kawamura and Toll and Srinivasan and Toll, at the same year, almost the same month, published in the same journal papers for the ablation of kapton using graphenes. That time the interest was to prepare conductive tracks on let's say polymer foils. Later the group of Srinivasan pioneered this laser-induced graphene production on kapton, and over the years people were ready to prepare porous graphene, which was patternable on polyimide foils with very low heat resistances. Although that time the term LIG, laser-induced graphene, was not popular, still the material was let's say explored and discovered several decades before the LIG term was coined. Between 90s and 2000, also the laser based micromachining of polymers was further developed, and research groups were able to prepare micro-patterned carbon for various applications, not so much related to energy, but mainly to electronics. At about 2012, in our group, we started working with the use of lasers to produce graphene, having working at time with silicon carbide wafers, preparing what is called epitaxial graphene, is a form of flat graphene useful for microelectronics, using a CO2 laser beam, working at ambient conditions. And later we also worked with other forms of silicon carbide, for example, different particles from nano to micro sized. And we have managed to decompose this material to its components, graphene scaffolds decorated by silicon nanoparticles. And this is the basis, let's say, that later we used and we are currently using in GRAPHERGIA for producing nanocrystalline silicon decorated graphene-like particles. At about 2012, from UCLA, the Canners group was the first one probably that used lasers to reduce GO and prepare microflexible interdigitated supercapacitors. There is a famous science paper for this work. And then in 2014, the Rice University, the Tours team, used the CO2 laser to decompose the polyimide, actually, and produce 3D porous graphene. But as I mentioned, this work was already done and known for almost 30 years before the Rice group did the work. But actually, the LIG term was coined at time, and the graphene, the laser used for graphene production, became more popular after the publication of the Rice group paper. So after 2014 and up to now, there are thousands of papers exploring different wavelengths, different atmospheres, and different substrates, different polymers, as Professor Spasenovic will show in his presentation. And the application portfolio has expanded to many sectors involving energy devices like supercapacitors, sensors, filtration membranes, smart textiles, etc. For historical reasons, this is one, let's say, seminal paper published, you can see here, 20 years before the Tours paper, where actually the Kapton foil was decomposed by laser beams, producing highly porous and highly conductive graphenes. That time termed glassy carbon, because the graphene term was not so popular, but the physics and the mechanism behind all the discoveries that followed during the last year was known since that time. Last year, our group developed a new technique and patented this technique where one can use a precursor placed at the distance from a substrate, and then graphene can be synthesized and simultaneously transferred to any type of substrate. So this differentiates previous works where graphene is, let's say, developed on Kapton and then needs manual work, manual transfer to take the graphene film to another substrate. In the way we developed this technique, we can produce graphene on different substrates, and the acceptor can be chosen across a wide range of materials, from, let's say, textile or polymer or glass or even ceramic. The form of graphene, as you can see here, is this three-dimensional foam-like. This is very useful for energy storage applications, and depending on the carbon source and the additives that can be applied to the carbon source, one can, in the end, obtain also graphene decorated with various types of nanoparticles. So as a last slide, I want to show that, as I mentioned before, that today a very large portfolio of laser-based techniques exist, with lasers spanning from CW wavelengths up to femtosecond, and from the UV to the mid-IR. And the term laser graphene processing includes processes like reduction, ablation, induction of graphene, patterning, etc. So lasers have turned to a very versatile tool for preparing graphene or graphene-like films on various substrates. And one of these applications is on flexible electronics, which will be presented now by Marco. So thank you very much for your attention. And I would like to invite Marco for the next 35-40 minutes to present his work on laser-induced graphene and MXenes.
Thank you very much, Spiros, for this excellent introduction. I didn't know some of the things that you showed, actually. And thank you for the invitation to give a talk here. So, as already introduced, I will speak about laser-induced graphene and MXene on polymer substrates for monitoring physiological parameters. The work was performed at the Center for Microelectronic Technologies, which is part of the Institute of Chemistry, Technology, and Metallurgy, or ICTM, here in Belgrade, Serbia. There we go. Okay. So this is the outline of my talk. I will briefly introduce laser-induced graphene. We just had a very, very nice introduction, but I will introduce it again. And then I will show how LIG, as we call it, can be used as a heartbeat and respiration monitor. Then I will discuss how we make this material on various biocompatible polymer substrates, including sodium alginate, PDMS-based substrates, polyurethanes, and polyimide-based substrates. And I will conclude with a short discussion about our most recent work on MXene sensors. Okay, so here is a bit about laser-induced graphene. My introduction starts a lot later than the one Spiros gave, because I didn't know about all the work that was done in the 80s and 90s. But indeed, this material became the most popular since 2014, since it was popularized by the group of James Tour at Rice University, where they showed, again, that you can, if you irradiate the top surface of Kapton, which is a polyimide tape, common polyimide tape, if you irradiate it with a laser beam, you can turn the top surface into few layer graphene or laser-induced graphene. Yeah, and the beauty of this is that it's quite easy to do. You just have to find the right laser parameters, and you can raster scan the laser to make all sorts of, well, any pattern that you want. For example, here they made an owl, which is a symbol of their university. And later they showed the same thing on various carbon-containing biological structures, such as toast bread, coconut, cork, and potato skin, which just shows you can make rapidly and easily custom designs of conductive designs on many different substrates. We set out to play with this material a few years ago as well, and we also started from Kapton, which we irradiate with the carbon dioxide laser, and then what you get is shown here in the middle. These are scanning electron micrograph images, and right in the center, this part B is the classical SEM image of laser-induced graphene. You see that it's sort of like a foam that has, so it's mostly a porous structure with walls made of few layer graphene. That's LIG. That's, I guess, the definition of LIG. If you zoom out a little bit, shown in part A, SEM image, you can see these lines from raster scanning the laser. We first made just rectangles, 2 by 1 centimeter, shown on the left. You see it on this yellow substrate. This is Kapton. And we just very crudely put 2 electrical contacts on this rectangle, and we found that it's extremely piezoresistive, this material, which means that if you bend it just a little bit, the resistance that you measure across these 2 terminals changes dramatically. And it's so sensitive that if you attach it to the forearm of a person, like on the vein, you can register the pulsing of the vein in real time. Hence, you follow the track, you track the heartbeat of a person. That's shown on the right here as changes in resistance in time. We have also transferred LIG to start, for starters, onto PDMS that's shown in the bottom left image. You can see a lot about that in the paper from 2022. We've also used the same principle to track breathing with graphene. If you attach the same type of device onto a person's chest, as the person is inhaling and exhaling, the chest expands and contracts, and you can register this in real time. Shown here, you get inhalation and exhalation in real time. Shown on the right is our sensor, our graphene sensor, integrated together with a very, let's say, rudimentary prototype of multisensory wearable patch where you register also the heart using ECG electrodes, body temperature, etc. So we have several different sensors integrated into one large device, but our LIG was part of that. And we quickly realized that Kapton is not the optimal substrate for these types of things. First of all, the Kapton tape that we generally buy has some glue on the underside. It's not something you want touching to a person's skin. But also, the Kapton tends to wrinkle easily, and it's not stretchable, etc. So we set out to explore what kind of polymers can we make graphene on using this method. Starting from polymers which we knew were biocompatible, looking for flexibility, stretchability, and usability. Yeah, often in the case of Kapton, graphene doesn't stick very well to it. It depends on the quality of the Kapton that you buy. So sometimes it just kind of falls off with use, which is not what you want. The first thing we did even before starting Project POLYGRAPH was LIG on sodium alginate. This is a material that is extracted from algae, and it's so biocompatible that yeah, it's often used as a food additive, so it's edible actually. And we found the correct laser parameters to make LIG on it, and we published that in this paper you can see here. It turned out that sodium alginate is not the best. Again, it's brittle. It becomes brittle after time. It absorbs moisture from the air. So we then wrote an entire project proposal. This was accepted by the Science Fund of the Republic of Serbia as a project. It's still ongoing. We have more than a year still to explore biocompatible polymers as a substrate for LIG. One of the first things we did also was PDMS-based polymers. PDMS is a very common polymer that is used in wearable devices because it's biocompatible, it's soft, stretchable, etc. But by itself, although it contains carbon, it doesn't seem to have enough carbon to make high-quality graphene from it. That's shown. The structure of PDMS is shown here, this large PDMS network. So one of the things we did was to add triton to it. Triton is a compound that contains aromatic rings that act as carbon sources to enhance the graphenization of PDMS. And you can see on the bottom these images here. As you add more triton, the LIG square in the middle, yeah, visually you can see already that it becomes darker. So it was our first indication that we're on the right track by adding triton, that we're probably forming better LIG. But of course, we characterize this with experimental tools. SEM, if you look, they all look good. They all have these pores. And then, for example, XRD, shown in the top right, you have this peak around 23 degrees, which is a graphene-related peak. And you can see that it is enhanced. It is larger if you add more triton. 30% triton in this compound is better than 1%. Then looking at Raman, at the bottom in the middle, you see, for example, the ratio of the defect peak intensity to the G peak intensity, so ID over IG, decreases as you add more triton, which is again an indication that you get higher quality graphene from adding triton. And the same trend is repeated if you look at the bottom right, this is sheet resistance measurements. You see that the sheet resistance will decrease as you add more Triton to the PDMS matrix and you optimize laser parameters to form Ligonit. And you get down to about 1.3 kilo ohms per square, which is not the best for electronics, probably, but it may have some other uses. One interesting thing to note is the wettability of this surface. So we tested that by putting a drop of water on these surfaces. If you focus on the bottom left two images where it says Triton 30, you see that without graphene, so this is just PDMS Triton. If you put a drop of water on that, it just spreads across the surface. You get this angle of 32 degrees. It's a hydrophilic surface. Yet if you add graphene, you get a super hydrophobic surface. Your drop just stands like a sphere. And I think it's interesting to see how that looks in real time. Here we attempt to put a drop on the surface, and it's so super hydrophobic that the ball just rolls off. However, if you are really careful and you align your sample carefully and do everything super correctly, then you can get the sphere to stay, and you see the water just stays there. So this can have interesting applications in water repelling surfaces just by adding graphene. One other thing we tried to add to PDMS is PEG, polyethylene glycol, this compound shown on the right here. It's also a carbon-containing compound. And you see, for example, bottom left photographs, PDMS is transparent. If you add PEG, it becomes opaque, and then you can form some kind of graphene on it, shown here in the middle. PEG is hydrophilic, but it's non-toxic, and it's a good carbon source. Again, we performed Raman spectroscopy to check the quality of this, and we see this trend again as you add more PEG to the PDMS matrix. You let's say increase the quality of the graphene, with the difference that in this case there seems to be an optimal content of 30 to 40% of PEG. If you go beyond that, your samples become inconsistent. They become kind of mushy, so it's not really something you can use. Here I show again SEM images. You see this flaky porous structure. It's very interesting, as Spiros said, probably for energy storage, etc. And on the right, we actually performed transmission electron microscopy to confirm that the lattice spacing here corresponds to graphene. This material is actually mechanically very interesting. We performed tensile testing. You can see that on the left. It has a very high Young modulus, like 0.5 gigapascal, and tensile strength is 2 megapascals, which yields to elongation and break 265%, which means you can stretch. It's very highly stretchable. You can stretch it to 2.5 times its length before it breaks. And it also has a high gauge factor, so it makes for a good bending sensor, which we utilized as an example to make this limb motion sensor. We attach this rudimentary device to a person's finger, and then as they bend the finger, you can register changes in resistance. It's a very basic demonstration of human-machine interface, but it's just shows what you can do with this kind of devices. And it's all biocompatible, it's stretchable, so we think it has some potential for use in wearable devices. Again, this is super hydrophobic. Without the graphene on top, you see that a drop of water will just spread on the surface. With the graphene, you get this really nice sphere of water just standing. This is useful for applications because it's sweat repellent as well. So leaving behind PDMS-based devices, we set out to make graphene on polyurethane networks. This is a different type of polymer, different class of polymer now that contains a soft segment and a hard segment. You can see that on the top is this long molecular chains. And then we can vary the ratio of the soft segment to the hard segment. And by doing that, tune the properties of the ligand. which is what we did. In the middle is shown a fabrication procedure. It's a little bit more involved, where you actually, here we induce the Lig on a Kapton tape, and then we transfer onto the polyurethane by spinning polyurethane on top and then peeling off the Lig from the Kapton to the polyurethane. We have two different ways of doing this. And then depending on the soft segment content, you actually get different transfer quality. Polyurethane is an amazing class of polymers. It has good biocompatibility. It's very non-toxic. It's highly flexible, stretchable. And what we found is that the adhesion of graphene to this is very strong. Once you transfer it, it will not budge. You can try to scratch it off, but it's very difficult. Here is a bit of characterization of the graphene made on these polyurethane materials. TM again confirms lattice spacing, indicating graphene. We actually, for this one, performed cytotoxicity tests, and we showed that the material is non-toxic. And it's highly crystalline. And then we also did EDX and SEM. You see that all the materials have high carbon content, but they all contain also a certain degree of oxygen. So there's a bit of graphene oxide there. And I think this is the case with most Lig that you will make. Because it's mechanically so favorable, this polyurethane, though it's stretchable, as I said, and flexible. Yeah, we've tested it as a wearable sensor for heartbeat. Now we no longer use the arms of human subjects. We actually have an artificial arm that has a real pulse. So a part of the arm pulses, and you can set the intensity and the repetition rate of these pulses, which is excellent for gauging these materials, the sensors based on these materials against one another. You can set the you can set the same intensity, for example, and see which sensor performs better. And this one performs very well. You see on the right, this heartbeat is registered very, very clearly. Signal to noise ratio is high. It's as we measured 270. And we found that the optimal soft segment content for this is 50%. You can see all about this in the papers that I keep citing at the bottom of my slides. We set out to synthesize polyimide-based materials. As I said at the beginning, and Spiros also said, Kapton is a polyimide, but a polyimide is a whole class of polymers. So you can tune it. You can tune the chemistry of this. You can make different types of polyimides, polyimide-based compounds, and by doing this, you can tune the properties of your graphene. Here we show that directly. So I will show you, this is the most complex synthesis that we did. It contains 3 phases. You have 2 precursors shown on this slide here. So we synthesize the first precursor shown in the top middle. And then from that, we synthesize the second precursor shown in the top right. And then from that, we can attach different crosslinkers to the end of this, attach it to the second precursor and get the final product, which is the polyimide. But just to show you here, we performed during these steps, these middle steps, we performed NMR and FTIR, but I will show NMR spectra of these polyimide precursors. And you can actually very, very clearly identify the bonds here. So it matches perfectly. And we know that these are, you know, we've done well our synthesis so that we can track our chemistry through this synthesis process. And then what we did was take the second precursor, yeah, that's the middle of the 3 steps, and then attach 3 different crosslinkers to the end. One is ethylenediamine, or ED, shown here in the top left, in top middle. The other is urea. And then at the bottom, you see something called APSA. I'm not going to try to read the chemistry, the chemical formula for that. But they're all slightly different, and they're all polyimides. And we managed to make LIG from all of them. It's a bit hard to see visually because these are very dark polymers. And you see the images here, but you can see a rectangle of graphene on this sample here. But it's more difficult to see than on the white polymers that I've shown you before. However, we noticed that the sheet resistance is quite low for this. It's better than we can get on Kapton, 3 times better in some cases, which is good for electronics applications. We perform again XRD, shown on the left. The big, let's say, yellowish or greenish curve is from Kapton. Kapton is a semi-crystalline polymer, and that's why you get these different peaks due to the crystalline structure or semi-crystalline structure. Our polymers are cross-linked polymers, which means they're amorphous. So you get this broad amorphous halo, yet on top of that, you get these very small peaks, 26 degrees roughly, which correspond to graphene. And we can measure the elemental composition, for example, from XPS. We see that these all contain, of course, highly carbon containing. They contain some oxygen, even though live on Kapton. However, our samples are designed and synthesized polyimides contain nitrogen, which is probably what dopes the graphene and yields these low sheet resistance electrodes. We did make electrodes from all of these, and we performed some basic electrochemistry measurements, but we're just in the phase of analyzing that, and I don't want to show anything conclusive at the moment. But they do act well for electrodes. I want to show that some of these samples have very good adhesion. For example, on the right top, you see if we put sticky tape on Kapton with graphene, with LIG, the LIG just comes off, and most of it comes off. However, for example, this APSA sample is quite good in the sense that LIG barely comes off, and the sheet resistance changes very little if you attach a strong sticky tape to it and remove it. So the adhesion is great, which is good for applications. We've performed detailed characterization of these samples, mechanical properties. Well, they're all different. Some of them have lower Young's modulus than Kapton. Some of them have much higher Young's modulus. The hardness also, some of them are softer than on Kapton. Some of them are harder than on Kapton. Plasticity as well. In terms of sheet resistance, these are electrical properties shown on the right. Again, some of these samples perform better than Kapton. Others have higher sheet resistance, which is not so good for electronics, but it may be good for sensing. And then on the bottom, you see SEM pictures. They all have this nice porous structure. It's a bit harder to see for the EDA sample because this sample has some polymer, thermally degraded polymer due to laser induction on top of the graphene, so it's hard to characterize. And the point is that with tuning this chemistry, you get different properties of the materials. Here we have a table such as this one, where we have most of the parameters that we studied, and then we put into the table which one of these materials has the highest value, for example, for stiffness, which one has the lowest value. Yeah, and then you can, for example, observe this one. I selected just one. To give you an example, this is the polyimide APSA sample with graphene on it. It has a very low stiffness and a very low hardness, so you can stretch it, yeah, and it's soft. So this seems to be a candidate for something you may put on a person's body, because we know all of these polymers are biocompatible. Its sheet resistance is rather low, so it could be used as an electrode, as a worn electrode. It's hydrophobic as well, which is great for wearable devices. Adhesion is amazing, as I've shown before. So this APSA device could be a good candidate for wearable electrodes based on LIG. for example. And others have their own favorable and unfavorable properties as well. Okay, so I will just switch gears. I will discuss a little bit MXenes. This is our even more recent work. MXenes are a class of materials which are highly tunable because you can functionalize them. And we produce ours using the mild method, which involves etching, delamination, and sonication, and then dispersion in solvent. And then from the solvent, you can deposit these MXenes on your polymer substrate. The MXenes themselves have excellent electrical conductivity and a high specific surface area, so they're reactive. You can use them for different things. We deposit them on polyurethane substrates primarily. So we prepare our polyurethane film shown in the top left. The thickness of this particular film is 0.5 millimeter, or 500 microns, and then we perform spin coating and different to deposit MXene, but we perform spin coating several times to optimize the thickness of the MXene. And then we get something again. So the polyurethane that we get has very good mechanical properties, high Young's modulus, high tensile strength, etc. And then you put on top of that MXene that is conductive. So we again perform such bending tests. These are bending sensors that we make, and you can see that as you bend the MXene, the sheet resistance that you measure changes. So it's a type of a strain sensor. MXene on a different substrate. This is PVDF, polyvinylidene fluoride. Also makes for a good sensor. Yeah, and this one we tested as a heartbeat sensor, again with this artificial arm, where we get again very high signal to noise ratios. You can see the clarity of the signal shown in blue here, the bottom right figure. So we have a whole series of papers now that you can also read about MXene, but most of the work is still in progress. We find these two materials, LIG and MXene, very interesting conductive materials to be integrated with polymers to make wearable sensors of heartbeat, limb motion, and respiration. This is just what we showed, but this is a whole playground of different possible applications. And what I like is that these materials are tunable. If you tune their chemistry, or if you tune the chemistry of the polymer, you can change the properties, mechanical and electrical properties of the final material, and then pick an application that you like. So this is what we do and what we will keep doing in Project POLYGRAPH. So I'd like to acknowledge the Science Fund, of course, which is funding this whole business together with our Ministry of Science, the Republic of Serbia, and many people who work together with me in the lab on the left. And we have one collaborator who is not from our institute, but from the Faculty of Physical Chemistry. And again, that I'd like to conclude, and thank you all for listening.
Excellent. Thank you so much, Marco. I see that the topic raises interest and a couple of questions that we have received from our participants today. So maybe we can go them through, and also I can pass the floor and open the mic to the people who wanted to ask these questions. And also, if anybody else wants to comment or react, you can raise your hand, and I'm able to also activate your microphone in this webinar. But with that, Marco, maybe you also see the question and answer box. So we have the first question from Moktik, who is asking, how does laser frequency impact the production of graphene, and does a higher wavelength correlate with improved quality and yield of the material? And then he has a follow-up question, but yeah, maybe we can start with that.
Yeah, it's a good question, of course. We only used carbon dioxide lasers, but we saw that people also use ultraviolet lasers. Some people use pulse lasers, picosecond and femtosecond. We don't. We use a continuous wave laser. these have not been quantitatively, as far as I know, gauged against one another. Maybe Spiros can correct me. But this is the league formation process is an interplay of heating and melting, I think, the top layer of the polymer, and then reforming of these bonds to form graphene also happens in an atmosphere. So I think it's very difficult to quantitatively, let's say, give a theory on how the wavelength would correlate with the quality and yield of the material. But people have noted that you can also change the atmosphere, maybe put a nitrogen atmosphere and dope the graphene, etc. Maybe Spiros has a better answer.
Yeah, thank you for your very nice talk. Also, this question is very, very useful. Actually, there is a very wide range of lasers used. There is no clear correlation, I would say, what is best or not. But I mean, we have used two types of lasers, Nd:YAG at near 1 micron and CO2 also in our lab. So depending on the material you want to decompose, it's important to match the absorption coefficient of the material with the laser, and then you need to do a fully optimized process across different parameters. Let's say graphene quality by Raman, heat resistance, as you showed. So you can have a equally, let's say, conductive graphene with a CO2 laser and the YAG laser also. What you change is probably the porosity and other properties. If you go to ultra-fast lasers, then you may go to what is called a thermal process. It's purely photoelectronic. If you go to, how to say, long pulse lasers or CW lasers, the effect is purely thermal. So actually, it's a very, very rich field for optimization with no yet very clear rules what is best or not. It depends on the precursor material and the application you would like to have.
Okay, so thank you for that one. So then the second question coming from Moin, what are the factors affecting the oxidation state of nanoparticles formed using LIG fabrication? Can we prevent MXene from converting into oxides by laser scribing MXene polymer hybrids?
Yes, the short answer to the second question is yes. We are not doing that yet, but you can laser scribe it to remove oxygen. But then again, this is best done in an inert atmosphere. So you want to fill your laser with with an inert gas while you do that. We haven't done it, but I think people have done it.
Brilliant.
So you can probably get lower sheet resistance if you try a little bit harder in this direction.
I activate the microphones from people asking questions. So if you want to have a follow-up question, you can just speak up. Okay.
Can I ask a follow-up question?
Yeah,
Sorry.
for sure.
Thank you. Thank you so much for answer. I have just a question that people are making the nanoparticles using LIG method. So they end up in making different oxidation states. Like in some cases it's cobalt oxide, and in some cases it's cobalt metal, and like that. And similar is the case with other transition metals. So do you have any work on that? Like how to control the oxidation states and what are the factors that can affect the oxidation state of nanoparticles?
Oh, we haven't done any of that. Maybe Spiros has, but
All right.
there's a lot in literature.
Yeah, we have tested few examples. Let's say depending, I think it mainly depends on the type of the material. For example, using a manganese precursor together with a carbon precursor, typically we get always oxide nanoparticles, for example, MNO, with let's say an ND-YAG laser. We have not tried with a CO2 laser, and then I think the temperature rise of the illuminated volume is also a factor that may affect the oxidation state. If you change, I mean, we have worked also with nickel. With nickel, we mostly get metallic nanoparticles, doing the same exactly experiment as with the manganese. So I think it depends on both, on the type of the metal and the proclivity of this metal to oxidize or not, and the temperature rise of the illuminated volume.
Thank you. Thank you so much.
Okay, related to this, I have a hand raised from Faizan Tariq. So normally you can speak up and ask your question, Faizan. No, we cannot hear you. I can see that also Moktik, you wanted to comment, so you can please free and you can speak up.
Yes. So thank you for that answer. I have a follow-up question regarding that particular point. So when you shine the laser on the surface, is that the surface has like a temperature rise only occurring at the surface of your polymer coating, or is it occurs throughout the matrix? And how does the thickness of our sample influence our the graphene formation?
Yeah, so the samples are thicker than the laser absorption volume. So basically all of the laser beam gets absorbed at the surface, and we make relatively thick samples. So microns, 10, 20 microns are the thinnest samples that we make, and your laser beam gets absorbed in the first couple of microns. So that's the volume that reacts with the laser.
So anything below 20 nanometer, 20 micrometers, let's say, so they would completely burn the sample. Is it what happens? Like,
you wouldn't burn it necessarily. You have to tune the laser power if you have a thinner sample. But we played with Kapton that was, I believe, maybe I'm wrong, 10 microns thin. You can make it, but then it's hard to manipulate this and make a sensor that is so thin and put it on somebody's skin. If you make the sample very, very thin, below 10 micrometers, like a couple of microns, it's just hard to manipulate, and we don't really see the point of that. But yeah, the heat dissipation would be different than in a bulk sample, let's say.
okay, thank you so much.
Marco, if I may add also to this point is, I mean, for the CO2 laser, what you say is correct. I mean, there is a strong absorption, so depending on the power, you can have a deeper penetration, let's say, and then you have a thicker graphene. For the case of ND-YAG laser, the absorption of a Kapton foil is about only 15%. So based on this very low absorption, we exploit graphitization of the bottom place, and this last technique, which it's our patented technology I showed in my slides, depends on the lower absorption of the laser. So the laser is mostly penetrating the film rather than being totally absorbed. So this can cause graphitization on the bottom side of the film, and this can create a graphene production and transfer at the same time. So depending to the question, depending on the laser source you are using, then you can change the penetration depth, and then of course you change all the properties of the final graphitized material.
Perfect. So let's go to the next question that comes from Diana from our sister project called Safari. So Diana is asking, how thick is the MXene layer you deposit with spin codes? And then the follow-up question. So maybe Marco, you can take this. And Diana,
yes,
you can also speak up. I have activated your microphone.
So spin coating will typically yield, I think, a few hundred nanometers of layers, but then we spin coat several times and we get micron thick layers. But really, you should check the papers that I cited for the details of this process. The rheology we haven't yet checked. The solvent, of course, plays a role. We dissolve in NMP, but you can use you can use water probably as well.
Okay, perfect. So then the next question comes from Andrea. Thank you for your very interesting talk and presentation. I have a question regarding the biocompatibility of the PVDF MXene sensor. Can this be exposed directly on the skin?
Yeah, PVDF is a biocompatible polymer as well. We always put the polymer side onto the skin, not the side that has active components such as MXene or LIG. Although we did show that LIG barely comes off or is very, very hard to take off on certain substrates. Nevertheless, that's why we use biocompatible polymers, because we put that side of the device on the skin and not the, let's say, nano side, or how would you call it, the LIG or the MXene side.
Perfect. Thank you, Marco. For this one, just speak up if you have follow-up questions. Otherwise, I'm moving forward. We have a couple left. So this one comes from Faizan. In the case of the Triton slide, the Raman spectrum shows a higher D-band intensity compared to the G-band, indicating a higher level of defects. However, for highly ordered graphitization, the D-band needs to be smaller. Also, we expect XRD peaks to appear around 26 degrees and so on. However, in the slide, the peaks were shifted. Do you want to comment on this one?
Yeah, so we didn't do XRD in-house. We outsource. We go to a different institute, and they have they have some lookup tables, and they claim that this is okay to have it around where we see these peaks. I don't know, but indeed the defect peak shown here is quite high, and especially when you add just a little bit of Triton. So I don't know if you still see the slides that I'm sharing, but the top curve is just 1% Triton, and that has a very high D-band. But as you add more Triton, the intensity of the defect peak goes down, and that's shown in the middle image. You see that the ratio of the intensities of the D peak to the G peak goes down as you add more Triton. But still, this is not something you can use as an electrode. The final sheet resistance is on the order of a kilo ohm per square. But we found that in general for any type of graphene-based device, not just LIG, but we also do liquid phase exfoliation. We found that if the graphene has around a kilo ohm to a few kilo ohm per square sheet resistance, it actually makes for a better sensor than those that have very low. I'm talking about chemical sensors, yeah, than those that have very low sheet resistance. So every one of these devices has a potential application. It's just a matter of characterizing it well and then selecting what that would be used for.
Okay.
Thank you, Professor.
Maybe two more questions and then we conclude the session. Munson is writing, thanks for the excellent presentation. My question, what are the limits of the prepared materials, Marco?
In the sense of what exactly? Limits?
Hold on, let me enable the micro. Okay, normally now, Munson, you can speak up. Okay, so no specification on that one. How about
Well,
yeah, go ahead.
He has another question later.
Yeah.
That's the last one, and maybe, yeah, you can send us an email and we can discuss further potential collaborations.
Perfect. And then to conclude, the question from Abhimanan, can we get monolayer graphene from LIG process and pulsed laser will form graphene on polymer substrates?
This I don't know. I think my personal opinion is that probably somewhere there is monolayer graphene, but we just don't see it. But I don't know what Spiros thinks about this.
It depends. If the question means monolayer on large scale, I think this is not possible. If within this porous structure you may have isolated graphene, yes, this is possible. Because graphene layers exfoliate also during the rapid thermal outgassing of the polymer. And the second part, yes, I mean, we're using ND-YAG, many people using ND-YAG lasers at 1064 nanometers. As I mentioned before, the absorption is only 15% for the Kapton. But yeah, you can do it also with this type of laser. You can prepare graphene with ND-YAG laser.
Okay, one final one to conclude. Have any of you tried the charge storage properties of LIG through PFM method?
Short answer is no. But Spiros has done some electrochemistry, and that's where we're heading as well. KPFM, you can just characterize the work function of the material, right? So I guess it yields it will yield kind of a number that gives you the potential for use in electrochemistry, but it's rather indirect. I'd rather just try the materials in an electrochemical cell.
Okay, perfect. Thank you. So with that, we are perfectly in time. So I would like to thank you, Spiros and Marco, for taking the time today, walking us through the laser-assisted methods your both labs are working on. Also, thank you all participants joining us today. We will share the recording as promised in our channels and via email to everybody who joined the session today. And you can keep yourself in the loop for the next scientific sessions we will be proposing in the framework of GRAPHERGIA. So with this, I conclude the session for the moment, and have a nice day, everybody. Thank you so much.
Thank you.
Thank you very much.